for the first thing, let's go through the syllabus. I'm gonna assume that you guys were able to see it, so I won't spend too much time on it. But if not, I'll drop the link in the chat right now. Did everyone see that link?
Yes.
Awesome. Yep. So here's the syllabus. As you know, since you're here, course is taking place Saturdays at noon EST. It's going to be 9 weeks. Recordings are going to be posted on our YouTube. Notes are going to be posted on GitHub. So everything's going to be easy for you to access if you can't make it to the lectures. Attendance is encouraged, of course. It's nice to have you here. It's nice to see the faces. You can ask questions live, but you're definitely welcome to do the course asynchronously. So we're going to want you to get a Planet, and we're going to want you to get in the Hooniverse group. That's where we're going to do Q&As and just support the students, release all the lecture notes and all of that. And there should be a mailing list. If you're not receiving the emails, please contact me on the network. I'm currently at this planet, Litsykes Tomter. This is a backup planet because my other planet is currently down, but it should be back up in a few days. But yeah, please DM me at this planet if you have any issues. Yeah, so about me, I was at Cornell doing a PhD in computer science. I was studying theoretical algorithms, and I'm interested in many areas of computer science. It's a really interesting project, and you know, I decided to leave that program. I didn't finish, and now I'm working for the UF. It's a really great decision for me personally. So yeah, I'm a recovering academic. Some of you might be, you know, programmers, have spent a lot of time working in this language or that language. So I don't have that much experience, but I'm going to try to teach you best I can. And I want to make everything clear and easy to understand. So if you need support, definitely reach out. I want everybody who wants to make it through the course to make it through the course. So we're going to have 9 homeworks. You'll have to turn in 8 to finish. Grades don't matter. As long as you made a reasonable effort on it, I'm going to count it as finished. If you finish the course, you get Agora, and you get opportunities to do stuff on the Urban ecosystem. I'm going to release homework after every lesson, and if you want prompt feedback, finish the homework within 8 days. Otherwise, you just have to finish the homework by the end of the course, by August 26th. So yeah, it's your choice if you want fast feedback or if you just want to do everything at the end, or wait on the certain homework till the end. That's totally fine. Okay. Office hours. So I'm gonna have office hours. You can come in and I can answer any question you want. I think I'm gonna have them twice a week, and I have a survey link to figure out the best office hours for the group. Oh geez, there's 5 people in the waiting room. All right. Hey, waiting room people. I'm just going over the syllabus right now. So the syllabus link should be in the chat. Let me know if you can't see it. And also there's a office hours survey. Please fill this out if you'd like to use office hours. This will help me figure out the best time to hold it for you guys. That's all in the chat. So yeah, let me know if you can't see it. All right. So yeah, the syllabus is available. The link is available. And that's pretty much all the important points. So I think I can get started with the lesson, unless there's any questions on this. All right. So let's get started with the lesson then. So as you know, this lesson is an intro to computing broadly and an intro to functional programming. What is computing exactly? The origins of computing go all the way back to humanity's search for truth. At least that's how I see it. Humanity wants to understand the world clearly and represent truth in unambiguous ways. For example, if we suppose that Madrid is in Spain, and if I live in Madrid, then I live in Spain. To all of us that understand English, like this seems like an unambiguously true statement, right? If you believe the premise. Aristotle was one of the first people to start thinking about the world in this way. He had statements like, if all men are mortal and all Greeks are men, then all Greeks are mortal. And there's another statement that just seems unambiguously true to us, right? The problem with most of the language that we use is it's slippery. It doesn't, most of the things we talk about day to day do not so easily fit into these kind of categories, these kinds of statements. For example, like everyone here knows what a chair is, right? But can you define a chair for me? And many of you may have seen this exchange on Twitter. So this person tried to define a chair. It says, chair is a separate seat for one person, typically with a back and four legs. Seat, a thing made or used for sitting on. Most definitely not circular. And then she said, this is a chair, right? So it's kind of silly, but it shows that, you know, it's actually really hard to use language to define things unambiguously. And to go back to ancient Greece, you know, I think Plato defined a man as a featherless biped, and then Diogenes held up a chicken and said, "Behold, a man." You know, so again, language is hard. So what can we start with as a foundation for representing truth in an unambiguous way? What is the basis of knowledge in some real concrete sense? I think the simplest possible thing we can do is express a difference to make a distinction. It is true that I have red hair, or it is false. It is true that I ate an apple today, or it is false, right? So yes or no. Two things in opposition. If we go to the Bible, the origin of Western philosophical thought, in Genesis, it says, "Let there be light." The first thing that God did in Genesis was to create light and separate light from dark. If we go to Taoism, we have the two primordial forces, yin and yang. And then from these two differences, we get 8 hexagrams, which represent different elements. And then we can get 64 even more complicated hexagrams, and then the whole, right? So the point is, in all of these philosophical traditions, we can find an origin which says the simplest possible thing we can do is make a difference between this or that, right? So that brings us to the bit. A bit is a singular value, which is 0 or 1, just a single binary choice. And this is a basis that we can use to make many, many things. So what can we do with a bit? We can represent more numbers, right? I don't have just 0 or 1 apple, maybe I have 8 apples. How do I represent that? Here's one way we can represent numbers using bits. So is this a good way? For example, the number 3 is going to be 0.00000001111111000111, etc. Right? So that is a possible encoding. It's unambiguous, but it's not a particularly efficient way to encode the numbers into bits, right? Oops. So the canonical way that we do this is going to be something called binary representation. And so for your reference, here's a table of some binary numbers. 0 is 0, 1 is 1. But if we look at 2, what's happening here is we're saying we have 1 thing in the 2's place and 0 things in the 1's place. If you look at 5, it's saying we have one thing in the fours place, 0 things in the twos place, and 1 thing in the ones place. So 4 plus 1 equals 5. And 16 is saying we have one thing in the 16th place and 0 things in all the other places. So this is pretty familiar, right? This is similar to how we normally represent numbers, except every entry is just 0 or 1, right? So again, this is a graphic of how 70 is represented. So one thing in the 64's place, one thing in the 4 place, one thing in the 2 place. Add them up and you get 70. So what about this sequence of bits? What does it mean? If I interpret it according to the scheme that I just showed to you, I might interpret it as the number 427,603, right? But what if I want to interpret it a different way? What if I say the sequence of digits 0110 maps to M, 0001 maps to A, 10010 maps to R, and 10011 maps to S? Then actually the sequence of digit says Mars, right? So it depends on the data doesn't just reflect what's encoded, but it depends on how you interpret it. So what if I actually told you actually C is 01101? Then the sequence of bits represents the word cars, right? So it's not clear, like any information needs a way for you to interpret it. But given that way to interpret the information, just using bits, you can represent anything. You can represent a number, you can represent words, you can represent a data structure, you can represent an image. It all depends on how you interpret it. So I'm sure many of you are familiar with images like these to represent computers, right? Your computer is a sequence of zeros and ones. Your orbit is a sequence of zeros and ones. Ultimately, it can be thought of as a really big number. Or you can think of it as an app or a game or a video chat with your friends. So it really depends on what this sequence of zeros and ones is interpreted as. But interpreted properly, it can represent any possible information. All right. So we've gotten an idea of how information is stored on a computer, information that might carry some meaning. However, a computer isn't just static information. It's not just a number or an image. It's something that's calculating, moving, doing manipulations, right? In particular, a computer is a thing that operates according to strict predefined instructions to perform tasks. You can ask your friend, like, please give me a glass of water, and they'll understand that and they can fulfill the task to some reasonable degree. However, when we're working with computers, we can't rely on this. We need to tell the computer precisely what to do. And that's what the essence of programming a computer is. So to understand this, we're going to study something called formal systems. And a formal system is defined as following. So first we begin with axioms. Axioms of a formal system are starting points that are facts that you assume to be true. Next, we have inference rules. Inference rules are operations that you can repeatedly apply starting from the axioms to build new truths. And finally, theorem is anything that can be reached by repeatedly applying the inference rules starting from the axioms. Does that make sense to everyone? If it doesn't, I'll show some examples next. So yeah. All right. So why is it important to study systems that are formulated like this? Well, suppose you can say that your axioms correspond to all possible states of a computer that you can start at. And your inference rules correspond to all possible operations that your computer can do. Then you can make statements like the following. This formal system having a theorem with a certain property is equivalent to this computer can reach a state with this property. Or this formal system has no theorem with a property that's equivalent to this computer cannot reach a state that has some property. And if you can say something like all theorems of this system have a property, then you can make a statement like all the states of this computer have a certain property. But remember that all of this depends on if you're able to make a direct connection between the axioms and inference rules of your system and the states and operations of your computer. And if you're able to do so, you can make precise, meaningful statements like this. So if we zoom out a bit and return to humanity's search for knowledge and truth, more generally, if you have a formal system and you believe that it accurately corresponds to some aspect of the world, then you can make correspondences like this formal system has a theorem with a certain property, then that's approximately equivalent to some property is true about the world. Or this formal system has no theorem with a property, then some property is false about the world. So what we're trying to do with computers is a special case of this. So let's go into an example of a simple formal system. So here's what's going on. Our system has one axiom, it's MI. That is the starting point of the system. And it has three rules to transform starting from the axiom. So rule one is given a string with the last letter I, the same string with the letter U added to the end is valid. Rule two is given a string starting with the letter M, you can double the substring after M, and that's also valid. And finally, rule three says, given a string with I as a substring, you can replace I with U and get a valid string. So you can imagine in your head, like MI is a starting point. And then all possible ways you can apply these rules after that produces like a branching out of all the possible valid states you can reach. All right, so can anybody tell me a theorem of this system?
MIU.
Mm-hmm. Yep, and how did you get to that theorem?
Well, I looked at rule number one, which states that if you have like an I as the last letter, then you should add, or like a U is also possible. It's added, and since we have an I,
Yep.
I was following the rule, just doing what I'm told.
Yep.
Yeah.
So he started from the axiom, and he applied rule one to get MIU, and that's a valid theorem of the formal system. All right, good job. So in general, here's an example of some derivations you might do. So MI is your axiom. Use rule two to double it, to double the substring to get MII. Use rule two again to double that to get M with 4 I's. Use rule one to add a U to the end. Use rule three to get rid of 3 of these I's and replace it with a U. and so on and so forth. So this is just one possible path you can follow through applying these different rules. I have another example of a formal system. So this formal system doesn't have one axiom. Actually, it has infinitely many axioms, and that's okay. So the axioms of the system are all strings of the form x, p, dash, q, x, dash, where x is any string consisting of only dash. So in particular, this is an axiom, this is an axiom, this is an axiom, and so on and so forth. These are all axioms of the system. And the rule of the system is if you have some string with something p, something q, something, you can add a dash to the second something and the third something. So here's an example of deriving some theorems of this system. So we start from an axiom. So dash dash p dash q dash dash dash. Let's check that that's an axiom, right? So x is two dashes, dash dash p dash q, and then two dashes and another dash, right?
Quick question.
Yes.
Why is x the dash? Like the last?
Yeah, so x is we're using x as a variable here.
Okay.
So, yeah. So in particular, this is saying x here and x here are a variable standing for some amount of x's, and they have to be the same.
For some amount or just like one dash? Or
a some amount. So it can be like 4 dashes, a million dashes, as long as it's the same for each x. That's different from here. So here we didn't use x, we use xyz to distinguish that these can be three different things. But here in the axiom definition, we use x twice to indicate that's the same thing.
Okay.
Yeah. Cool. Yeah, questions are good. All right. So we just confirmed that this is an axiom. We can use the rule to add a dash here and add a dash here, and that's a theorem. We can start from this different axiom or this different axiom and add a dash here, or sorry, add a dash here, add a dash here, and keep doing that. And it's kind of a boring system, right? But there's actually something interesting about this system. So how many dashes are on the left of P here? 1, 2. How many dashes are in the middle? 1. And how many dashes are on the right? 3. So 2, 1, 3. How about here? So 2, 2, 4. And how about here? 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5, 6. So there's an interesting property about every theorem of this formal system. So there's an interesting property here. So let's look at this one. 1, 2, 3, 4, 5. 1, 2. 1, 2, 3, 4, 5, 6, 7. So does anybody recognize the interesting property of this all true theorems in this formal system?
I have a guess that I feel like the rule here is when you apply the rule, the result of that rule is a new axioms.
Oh no. So for example, like this is a number 1 here is an axiom, right? But number 2 here is what you get from applying the rule to the axiom once. But it's not an axiom because an axiom is something that has 1 dash between the P and Q and has the same amount of dashes before and after plus 1 on the Q side.
I see. Yeah. So yeah, the axiom is always one dash between P and Q. Got it. Got it. Yeah.
Yeah, and 1 dash between, and then just 1 more dash on this right side than on the left side. So those are all the axioms. But for example, this one has 2 dashes in between, so that's not an axiom, but that is a valid theorem that we got from this axiom by applying the rule. So you notice I was counting the number of dashes. Does anybody notice the interesting property about this formal system, about the number of dashes?
You
Yes.
you add the same amount of characters to between P and Q and after Q every time.
Yep. So it's always the case for every theorem of the system. It's always the case that the number of dashes here plus the number of dashes here equals the number of dashes here. So that is in fact true. And you can even interpret this a certain way as a simple computer, which by applying the rule from all the axioms, outputs all true facts about adding 2 positive whole numbers. And we might even interpret P as a plus and Q as an equals. So we might even look at this and read it as 2 plus 1 equals 3, or 2 plus 2 equals 4, or 5 plus 1 equals 6. Right. So that's kind of interesting. But we have to be a little careful too, because, for example, this doesn't mean that dash P dash P dash Q dash 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 is a theorem, because even though it's true that 1 plus 1 plus 1 equals 3, this is not something that was created from just the mechanical output of the system, from the repeated application of rules, because you can never get these 2 P's. So you can't add things. You have to be careful not to add things from your interpretation, basically. All right, so were there any questions on that? All right, so I will be moving on now. So we have one final formal system, and this is going to get us all the way to what is functional programming. So in this system, let's first start with the axioms. N is an axiom for any number n. So like 1, 100, 1/2, -1,000,000, whatever. Those are all axioms. Also, add AB, sub AB, mul AB, div AB are all possible axioms where A and B are axioms. So there's a recursive definition here. So let me show you some examples. So 5 is an axiom, 167 is an axiom, mul 2, 3 is an axiom, and this one where add the result of mul 2, 3 to 5. This is also an axiom in the system. And we also have some rules for the system as well. So we got 4 rules, and judging by how you might read this, they're pretty straightforward. So we can reduce this tree with add AB to the number that is just A plus B. We can reduce this tree with sub AB to the number that is A minus B, and so on. As long as the A and B are numbers, not a tree, because you couldn't, right? How do you add or subtract a tree, right? So they have to be numbers. And here's an example of a derivation, starting from an axiom and applying some rules. So applying rule 3, reducing multiplication, we reduce this to 6. And applying rule 1, reducing addition, we reduce this whole thing to 11. So this is an example of a computation. So what exactly is a computer? You sit down to a computer, right? And the computer doesn't know what you're going to do. The computer can't tell you to do a particular thing. It's waiting for an input, right? It has some buttons. You might click this button or that button, or it has a form, and you might put some number into the form or some words into the form or whatever, right? The point is the computer doesn't know what your input is going to be, but for whatever input you give it, it's expected to do some process and then produce an output. So the key thing here is that a computer is something that is waiting for the input. It doesn't know what the input is, but when it gets it, it'll have an idea of what is the computation I'm supposed to do, and it'll give you an output, right? So how can we model this idea in a formal system? So how about this, right? This is pretty similar to what we just saw, except there's an X here, right? So what is the value of this? Can we apply our reduction rules to this? If you'll recall, our rules are, these are the rules, right? If A, B are numbers, we can do something. So can we apply our reduction rules to this tree?
Yeah, you just can't simplify X and 3, but
well, this isn't a number, right? So you can't do this because this isn't a number. You can't do this because this is a number. It's just X, right?
Yeah.
Yeah. So there's nothing we can do here. It's waiting. It's a form that's waiting for some input for the X. Once you give that X, then we can perform the computation and it'll assign a particular output for that, right? So for example, we might substitute X equals 10. And you might think of this as you did something, you did some action on your computer. You gave your program some input. And then once it gets that input, it knows, first I need to apply rule 3 to reduce the multiplication, multiply 10 by 3 to get 30. Then I apply rule 1 to add 30 and 5, and I get 35. And then it gives 35 back to you, right? So we did a substitution with a number for a variable, but we can even substitute expressions for variables. So here we have X is the expression sub Z1, right? And then we have this expression mul YY. We can sub X in there. That's completely fine. And then we get this more complicated tree, right? Then we can substitute a number for 9. After doing that, we get a tree which has no more variables. And at that point, we can apply rule 2 to reduce this subtraction to 8. We apply rule 2 again to reduce this other subtraction to 8. And then we apply rule 3 to reduce this multiplication to 64.
Very satisfying.
Yes. So, but we also don't have to do it in that order either. This is the same operation. We have X is sub Z1, but we can substitute Z first. We can substitute Z into X, apply rule 2 to reduce that, and get 8 is X of 9. So 8 is what we got when we gave X an input of 9 and bound this Z. Then we can substitute X of 9 for Y into the multiplication, use rule 3 to reduce the multiplication, and then we get 64. So we got the same thing, but we were able to perform these substitutions in a different order. So does that make sense to everyone?
I think you could go over one more time for me. It was a little.
Yeah, sure thing. So here, we have x is this expression. X is an expression sub z1, right? And then we have another expression, mol yy. So we have these two expressions, right? And we're going to compose them. One thing we can do is take x and find its variable and evaluate x first. So we substitute 9 for z in x, take x to sub 9, 1, use rule 2 to evaluate this tree, get 8, and that's your value for x evaluated on 9. And then you can take that and substitute y for that into y in mol yy, use rule 3, and then get 64. Or you could have substituted this expression with a variable in it first without putting any numbers into anything yet. So you substitute this tree into mol yy, and instead of these y's, you get these subtrees, right? And then you substitute 9 for z. And then you can just apply the rules to reduce this tree all the way down to 64. Was that clear for you, Alex?
I think so. Yeah, I think so.
Okay, great. All right. So why did I introduce you to these trees and this arithmetic? I just introduced you to the basic ideas of functional programming. Functional programming is a way to think about programming where everything is a function, a map taking inputs and giving you outputs. So here are the diagrams we just wrote, but written in a functional language pseudocode, right? So we have fun1, it takes a z and it computes z minus 1. Fun2 takes a y and it computes y times y. And what are we doing here? Well, we're composing two functions. We're saying, give an input to fun1, get the output of it, and feed that output as the input to fun2, and then compute fun2 on that. So what are we doing when we plug in 9 here? We have 9. It's fed to fun1 of z. That gives us 9 minus 1 is 8. That 8 becomes the y as the input for fun2. Then we get 8 times 8, and then we get 64, right? So in pseudocode, this is an expression of what we just did with the diagrams. Does that make sense to everybody?
Yes.
Okay, great, awesome. So many of you might be familiar with programming in an imperative language, right? So what if you're trying to compute this in an imperative language? What would you do? So you in that paradigm, you have a state, and you tell the computer to do things. You say, do this, do that, and then do that, right? So in pseudocode, it might be take input z, set z to z minus 1, set z to z times z, output z, right? Like that's kind of like a pseudocode for how you might do things in like C or Python. And if you want to combine things, you just sequence them, right? So to understand functional programming, we have to stop thinking in this way. We have to think about it as functions from inputs to outputs. If you want to combine operations, you don't sequence them, you pipe them. You take the output of one function and feed it as input to another function. And you can do this as many times as you like, right? And the idea is combining functions in this way composing functions gives you another function. If we go back here, we composed fun1 and fun2, but this whole thing is a function. We made a new function by composing two functions. So here's another way to write it. Functions can call other functions in their code. That's perfectly fine. So here we have fun1 of z is z minus 1. This is the same as before, right? But here we define fun2 of y as compute fun1 of y and multiply it by computing fun1 of y. And so when we plug in 9 to this, it's the same thing. We get 64. But the different thing is that we actually use the definition of fun1 in the definition of fun2, right? But we have something even more interesting. A function can even call itself in its own definition. This is something called recursion, and it's an extremely important concept in functional programming. Okay, so let's consider this program right here and figure out what it does. So what is function of 0? Can anyone tell me what is function of 0?
It's counting down to 0.
No, what is, so function takes an n. I'm going to substitute 0 for n. So what is the output of this function on the input 0?
0.
Yes, yes, good. Yes, exactly. Good, David. Okay. So what happens to this when we plug in 1 for n? So we plug in 1. If n equals 0, 1 does not equal 0, so we skip this. And we go to this branch. Then it says function n minus 1. What is 1 minus 1? It's 0. And what is function of 0? Yes, f of 1 equals f of 0 equals 0. Great. And what is f of 2? Yes. So there's no counting down. There's no counting down. We're just thinking of a function. So a function is saying, give me some input. What is the output? So what I'm asking is, given an input of 2, what is the output? And I guess you can think of it as, in a way, the process is like counting down, but we have to, I think we have to get in the mindset where it's input and output. Yes, it keeps working till 0. So for any positive whole number, this is going to return 0. Okay, so that's pretty straightforward, right? But what about this function? Okay, this is also a recursive function. Or did everybody understand what was going on here? This is a very important concept. If you're confused, please let me know.
What concept are you referring to? Are you mean like recursion?
Yeah.
Oh, cool. Yeah.
Yeah.
Yeah, it makes sense. Yeah.
Okay, awesome. All right. If there's no objection, then I'll go on. So let's consider this function. So what does this function do? Well, let's consider the input 0. If we give it 0, if 0 equals 0, return 0. That's fine, right? What is this function output? Or does it output if I feed it a 1 as an input?
It would never stop, right?
It never stops.
It would never return.
Exactly, it never returns. Yes. Does everyone see why this function would never return a value? Can I go? Yes. So if I feed this function a 1, it's going to say if 1 equals 0, no, 1 is not equal to 0. So then I go to this else branch. Else function of 1 plus 1 is 2. What is function of 2? We don't know. So let's figure out what function of 2 is. Function of 2, if 2 equals 0, 2 is not equal to 0. Else, function of 3. Well, what's function of 3? We don't know. So we have to figure out what it is, and then we have to figure out function of 4. And if there's no point at which this loop terminates and pops back up and gives you an answer.
Yeah, it looks like there's 2 branch, but the funny thing is one branch just keep referring to itself. It doesn't, yeah.
You never get to a return.
Yeah, exactly. So it's okay for things to keep returning to themselves if at some finite point there's some solution at the end and that pops back up and gives you an answer. But here that doesn't happen. Here it happens because you're always counting down, you're going to hit 0, but here it doesn't happen, right? All right. That makes sense to everybody?
Yes.
All right. So now let's consider something called time complexity. So in programming, it's important to consider how many operations does it take to compute a result. So going back to this example, how many calls to the function does it take to compute function of 0?
1.
Yes, good. How many calls to the function does it take to compute function of 1?
2.
Yes. And how about function of 2?
3.
Yes. So can we write a mathematical expression relating the input n to the number of function calls it takes for this to return an answer? Yep. So n plus 1, exactly. So this is something we call in programming O of n, or the time it takes for this to return an answer is linear in the input n. Let's consider another function. So it's O of n time. All right. Here's another one for you guys. All right. So first, let's figure out what this function does. Okay. So what is this function output for 0? For an input of 0, what is the output?
0.
Yes. Right. All right. So what if I give this function an input of 1? So it's going to say if 1 equals 0, no, it's not, right? So else return function of n minus 1 plus function of n minus 1. 1 minus 1 is 0. So this is going to say return 0 plus 0. So this returns 0, right? So function of 1 returns 0. Yep. What does this function return for an input of 2? Yep. So for an input of 2, if 2 equals 0, 2 is not equal to 0, so we skip this. Else return function of n minus 1 plus function of n minus 1. What's n minus 1? 2 minus 1 is 1. So we're returning function of 1 plus function of 1. But we just covered what was function of 1.
It's still 0, right?
Yep. But yes. So what is function of 3? Can anyone tell me what this returns for an input of 3? Yep. Yep. So if we think through this, function of 0 is 0. Function of 1 is 0 plus 0 is 0. Function of 2 is function of 1 plus function of 1, which is 0 plus 0 is 0. Exactly. So whatever input, whatever positive integer input you give this, it returns 0. So this is doing this function, the same function that's represented by this one. It's the same function. Does that make sense to everybody? But what's the key difference here? So let's think about the time this takes, right? So how many calls to the function does this take to return for an input of 0?
1.
Yep, 1. How many calls to the function does it take for an input of 1? Well, if we give it input of 1, we skip this branch, we go here, and we call function of 0, and we call function of 0 again, and we add them. So that's 3 calls, right? So for an input of 1, it takes 3 calls. What about an input of 2? What happens? How many calls does it take if we give this an input of 2? Well, 2 comes in here, 2 is not equal to 0, skip this. Then it says return function of 2 minus 1 plus function of 2 minus 1. Well, that means we need to compute function of 1 twice. And we just learned that function of 1 takes 3 calls, right? So to compute function of 1 twice, it takes 6 calls plus the original call is 7 calls, right? So for an input of 2, this is taking 7 calls. And I can do the math out, but for input of 3, this is going to take 15 calls. So this is growing very differently than the one before. In fact, it's growing exponentially. For an input n, it takes on the order of 2 to the power of n calls for this to finally return a value. Yeah. So that's something we want to avoid in programming, because that number, exponential growth, it grows very, very big, very quickly. So it's kind of interesting that this function turns the same thing, but it just takes much longer time to do it, right? So we pretty much covered the important basics of understanding functional programming and getting you to the starting line for learning Hoon. What I'm going to do next is I'm going to cover some things that are important to working as a software developer. So just writing code, saving your code, working with others, stuff like that. So I'm going to share my screen here. So how you write software is generally in something called IDE, or an integrated development environment, right? This is somewhere where you can write code, save it. Maybe it tells you if you have bugs, or it tells you if the syntax looks weird, or stuff like that, right? Technically, you could even write in like a text editor, but that doesn't give you any tools to help you. The one we recommend for the course for writing Hoon is VS Code or VS Codium. I'm going to type those in the chat.
What's the difference between these two?
Yeah, so VS Code is the Microsoft version, and VS Codium is open source. So if you like open source software, go for that. That's what I use. But functionally, they're the same. So, but the nice thing about VS Codium or VS Code is there's Hoon support for it. That's why we recommend it. So oops. So here's a Hoon file. It has syntax highlighting. So it's going to highlight, these are called runes. It's going to give those a different color. It's going to give this a different color. It's going to give, these are types. It's going to give this a different color. So not necessarily every editor can have these capabilities. So that's why we recommend VS Code. And also there's a really useful utility called Hoon Assist, which you can install. So what that does is you mouse over this rune and it provides the doc for that rune right here. So that's pretty useful, right? The way you get these utilities is they're in the VS Code store. I'll have them linked. They're linked. They're going to be linked in the syllabus and also in the lecture notes. And you can install them. If you have VS Code, you just install them from the store. If you have VS Codium, then you need to do this thing where go to extensions, and then you download the file and you install from V6. But yeah, so here are the two that I have installed. These are super useful for writing Hoon. Besides that, like, so you write stuff in here, you save it, but this is all on your local on your local machine. The super important tool that people use for coding is called GitHub. I assume that many of you are familiar with GitHub. Some of you may not be. It's basically just where people store their code, where they push changes, where they work with other people, where they back up previous versions. This is an indispensable tool for coders. So if you go in here, this is called a repo. This is like a project, and you have like code in here, and you can push your code to the remote repo, and people can view it and borrow it and all that stuff. So if you haven't used it before, there's going to be a homework question for you to get a GitHub set up and just do some basic stuff on it. And I think that brings us to the end of the lesson. Are there any questions on anything, either development stuff or just the general computing stuff that we covered?
No, but I want to say you did a good job.
Oh, thank you. Thank you. I appreciate that. Use the one from Tlon. I think that one's more up to date. Yeah. All right. Yep. Oh, one last thing. One last thing. I have a anonymous feedback form. I'm going to release this after every lesson. So just if you want to give me anonymous feedback, good, bad, ask questions, whatever. If you ask questions, I might even answer them in Hooniverse if you want. So just whatever you want to tell me anonymously, feel free to go type it in there. And if you want to tell me something non-anonymously, of course, you know how to contact me. So yeah, I'm very open to feedback, very open to making this course better for everybody. So yeah. All right. And I'm going to link the syllabus again, just in case people miss that. Important document. Yeah.
Is the only homework just getting GitHub set up?
No, there's more homework questions. I'll release it within today.
Okay,
Yeah.
cool.
Yep. And so there's office hours survey. All right, so, and I think that's pretty much it. So I'm going to stop recording now.